Hey, Marty, what are you doing?
I'm building a model of the Mars rover Curiosity.
Cool.
It is so cool. Could you imagine being on the red planet, roving around, looking around at all of the geologic features and all of that science that's going on?
Yeah, I can imagine that, but can you imagine the entry?
Yeah, that might be a little fiery, I guess. Well, do you want to help me build this?
Sure. How long is it going to take?
It's probably going to take a little bit longer than 30 minutes. Video guys, can you help us out here? See? That wasn't too hard.
No, I think we've got plenty of time for the show.
This is STEM in 30. This is STEM in 30. Hi, I'm Marty.
And I'm Beth.
Today we are coming to you live from the National Air and Space Museum in Washington, D.C. We are inside a gallery called Exploring the Planets.
We want to begin by welcoming our online audience. We invite you to submit questions. We have an expert who can answer them for you, and we may even take one on air.
Now this gallery is incredible. There are some great artifacts here. One of my favorites is the blink comparator that you see behind me. In 1930, Clyde Tombaugh used this instrument to find Pluto. Percival Lowell had predicted where Pluto might be, and Tombaugh, using this and photographic plates, looked through images for months to try to find Pluto. See how hard that was? Check out these images. Now, as you see these images, do you see Pluto there? It's kind of hard to spot. You see why it might take months. Now look what happens when we add a couple arrows. Do you see it now? So if we add some arrows here, you're going to see Pluto drawn out a little bit more. Obviously, you can see why this may have taken Tombaugh months in 1930 to have discovered Pluto.
Speaking of Pluto, New Horizons, the object above me, was launched in 2006. In 2015, it flew by Pluto and took some fabulous photographs, only 8,000 miles above the surface.
All right, one of my favorite stories to tell in this gallery is that of Voyager. You see the full-scale model up above me. This spacecraft was launched in 1977. There were actually two of them. They're still going and sending back signals. Now, on board was a golden record. A record is a thing that we used to use in the olden days to record sounds. And on this record, we sent sounds of Earth out into space. Listen to this.
Konnichiwa. O genki desu ka?
Hello from the children of planet Earth.
Hartelijke groeten aan iedereen.
And now I am joined by Michaela and Caleb. Mackenzie, I'm sorry, and Caleb. Now, we're standing here in front of the Mars rovers. We're actually going to be talking about Mars today. Now, why do you guys think that we would send these rovers up and not astronauts?
Because they have little cameras and wheels.
Little cameras and wheels. Did you guys get a chance to take a look at these things? Now, did you notice anything that is similar among them? You got it. You need the mic. Go ahead.
They both have little gold pieces, wheels, and solar panels.
Gold pieces, wheels, and solar panels. Now, the rovers are specifically engineered to do certain things while they're on Mars. And is there anything that you notice that's different?
One's bigger and one's smaller.
One's bigger and one's smaller because they do different jobs. Now, to learn more about the jobs that rovers do on Mars, let's go to Marty with our first guest.
Thanks, Beth. I'm joined today by Kobe Boykins, a mechanical engineer at the Jet Propulsion Lab. Thank you so much for joining us today.
Thanks for having me here, Marty.
So those guys did a great job.
They did an awesome job.
And they noticed a lot of different things about the rovers. When I look at the rovers, I notice that the wheels are very, very different. Why is that?
Yeah, so if you look at the rovers that you guys have here, which is awesome, you start off with Pathfinder, which is a small rover. It was a technology demonstration. We wanted to actually see if we could actually drive on the surface of Mars. We didn't know if we could do that or not. And so if you look at the wheels specifically, you'll see that the wheels are very sharp. The texture of the wheels looks totally different. And that was so that we could climb over rocks. But as we got better and understood more about what the surface of Mars was like, we actually went to the Mars Science Laboratory. Its wheels are a little bit bigger, and they're designed more not to climb over rocks, but to drive over loose dust. Think of it as like light, fluffy snow, if you will. And that's how they were designed. And then you get to Curiosity, the one that's behind us, and it was a much larger rover. And its job really wasn't, it wasn't worried about rocks because, the rocks were going to be small compared to the size of the rover. It was really actually to climb up Mount Sharp, which is where we landed in the Gale crater, to do more investigation. So you can see sort of the history and the development of the wheels and how we've changed from rover to rover.
Now, there's a feature on the wheels that I think is really interesting. There are some holes on them, but they serve a purpose, right?
Yeah, so there's what we call the odometry feature. And so odometry is just distance. And what we can do is we use that feature to actually, after we drive the rover, we know how far we told the rover to drive. And we'll turn around and we'll take a picture, and from the picture we can see how far we drove. That helps us tell a slip. But the interesting thing about that feature is when we first started off designing the wheels, we actually wrote the words JPL sort of a negative so that we could actually stamp JPL on the ground, on the surface, so that we could see, JPL on the surface of Mars, which would be really cool. But we actually had to change that. So we actually turned it into Morse code. And if anybody knows Morse code, it actually says JPL in Morse code. So it's really sort of a fun thing about being one of the engineers and design people behind it, that you can do things like that and sort of make it fun as well.
But it still serves a very important purpose.
Very, very important mechanical purpose and something that we use for science as well.
Now, did you learn things when you were working on the first rover that helped on the second and the second that helped on the third?
Yeah, most definitely. In fact, we actually started the rover program a lot before the first rover, which is Sojourner on the surface, or here that you guys have in the museum, which is awesome, is the Flight Spare Marie Curie. And so that was really the start of it. And you can see sort of the evolution of the rover. So Marie Curie or Sojourner was really a technology demonstration. Just drive. Take an image of the landed station and Carl Sagan Station. Spirit and Opportunity were the first time where we actually were, that was the primary mission, was the rover. And they're roving geologists. So their specific goal was to go look at the history of the rocks on Mars and see if Mars was once a wet place. And then you get to Curiosity. Curiosity, and not being a roving geologist, but a roving biologist. Her job was actually to see if Mars was once a habitable place, and had life started on Mars, would it be able to be sustained on the surface?
Awesome. They've all got very different purposes, and you can see that in the models here.
Yeah, most definitely.
That's cool. You ready to take some questions?
Yeah, sure, let's do it.
All right, let's start with an online question. What was the biggest challenge your team faced when engineering Curiosity? That's from Mark.
Okay, so Mark, it's a fantastic question. What was the biggest challenge that we faced? Well, for me personally, I was part of the engineering team that built the actuators for Curiosity. And so the actuators are things that move. They're like motors, if you will. And so everything that moves on this vehicle was actually was my responsibility at some level, my team's responsibility. And so we had to make sure that we understood how it worked and how it was going to give us information, make sure the vehicle was going to perform appropriately on the surface of Mars. And it was a very, very long development. We had some failures, some things that didn't work out perfectly. But at the end of the day, we got the vehicle to the surface of Mars, and it's been working perfectly. So thanks for that question. It's a really good one.
Awesome. All right, Jack, you've got a question?
Come on up, Jack. Here you go.
How does the rover take pictures?
Oh, how does the rover take pictures? Actually, it's a great question. So the rover actually has quite a few cameras on it. And a lot of the pictures that you see actually come from what we call the remote sensing mast. And on there we have some really, really good cameras. And it's interesting, I was just reading something here in the museum. It's called the charge couple device. That's the detector behind the camera. So we take pictures almost exactly the way you do with your cell phone. And that's what we take that image and then we relay it to one of our orbiting spacecraft. And then that gets relayed back to Earth. So that's how we get pictures on the surface of Mars.
Cool.
Yeah, yeah, thank you.
Great question. All right, well, one of the things that we've done by being able to drive around the surface of Mars is learn some incredible geology. Let's go over to Beth with a Martian geologist.
Now I'm joined by Dr. Jim Zimbelman, who is a geologist here at the museum. Jim, thanks so much for being here. We've been roving around on Mars for a long time. Why? What have we learned?
Well, geologists like myself love the pictures, but we always see in a picture, gee, I'd like to get closer to that. That's what rovers have allowed us to do, beginning with the little Sojourner, then to Spirit and Opportunity, and now with Curiosity, we can go right up to the rocks and examine them in detail. The things that interest me are sand, because each little particle is telling us something about the rocks in the vicinity. So they are giving us different views as we move along a beach or in a sand dune or something like that. Well, that turns out to be true at Mars, and we now know that because just the end of January of this year, Curiosity, for the first time, investigated an active sand dune on Mars with all of its instruments. I've waited over 30 years for this to happen, and it's just terribly exciting to finally see some of that new information being revealed. Not only the pictures that show us some of the detail, but Curiosity has instruments that tell us the chemistry and the mineralogy of the little sand grains and can make other measurements that we just hadn't dreamed of decades ago when we were wondering how could we get to a sand dune on another planet. Now, so far, there are a variety of ideas as to what's going on. It seems to be like a sand dune we're used to thinking about here on Earth, but the conditions are different enough that the ripples look a little different, and that will need to be explored more. But again, the advantage of a rover being able to take us and our instruments right up to an area and investigate it in detail, that's terribly exciting.
Thank you so much for joining us today.
You're welcome.
Now, one of the ways that we learn about that geology is through the cameras.
Right.
And nothing seems like it's by coincidence, and the height is in the same boat, right?
No, nothing's by coincidence, and all of it's engineered, all of it's designed. And so for Spirit and Opportunity, the Mars Exploration Rovers, the cameras are right at 5'2". And the reason we did that is that's the average height of a human being. So the images that we get back from the surface are like somebody was walking along the surface looking out at Mars. So it's like a human being was really there. With Curiosity, they're a little bit higher than that, but we still wanted to give that same sense of a human being actually roving the surface so that they could look around and scientists could actually get a sense of what does this rock look like or what does that rock look like, this geologic feature or that geologic feature. And it actually helps with analyzing the data that we get.
Now, did you guys have any challenges when you were designing the cameras and building them?
Yeah, the cameras are pretty difficult in general. And one of the most amazing things is that with the cameras, and we separate them a little bit, just like your eyes are separated, so you can do interferometry. More or less what you can do is you can tell depth. One of the things that you have to be able to do is know where those cameras are. And so because Mars is so cold, it can actually get to minus 128 degrees centigrade on Mars. That's the temperature at which carbon dioxide freezes in the atmosphere. So you could have dry ice on the surface. And then it gets pretty warm. It can be about the temperature that it's in here, so like 72 degrees Fahrenheit or 20 degrees centigrade. And so you get metal, and metal will move when you have temperature swings like that. So you have to be able to understand how do those cameras move and distort on the metal that they're mounted to, and then take that out so that you can actually make a 3D image that actually works.
So you guys not only have to take account getting it to the planet, but also anything that's going to happen once it's there.
Once it's there and how it points and all of the things that go along with it.
Wow, that's really cool. Now, the cameras on the Mars rover have taken some absolutely amazing pictures. Check these out.
So you were talking about taking pictures on Mars.
I
Now,
was.
when we take pictures here on Earth, we have a bluish atmosphere.
Right.
And that influences the colors that we see.
Right, most definitely. It's how our eyes work.
But on Mars, things are a little different.
That's correct. And you have something that looks like Mars, actually, when you look to it, right?
So yeah, so what is different about taking pictures on Mars than taking...
So Mars tends to be a little bit more red, or red in the spectrum of light that we see than we see here on Earth. So mostly because of the atmosphere and the dust that's captured in the atmosphere.
Okay, so we're going to take a look at these rocks.
Yeah, so everybody look at the rocks.
So we're looking at these rocks. Now, this is the way we would see them on Earth.
Right.
And this is similar to the way we would see it on Mars.
That's exactly right. So what you can see is when you look at that through that filter, through that sort of rosiest color filter, you actually start to lose some of the definition in the rock. So our eyes are built to see a lot of different depth of field and different things, and you can actually look at those rocks and see different pieces. But with the filter, it actually starts to dull some of that out. You don't see that contrast as much.
Now, how do we look at these images from Mars in a way that we can understand and see things that we want to see?
So what we do is we actually use different filters, just like what you had, and we put those in front of our camera, and we actually take images that have different wavelengths of light. So you can think in the color spectrum, what we see is actually a very, very small bit of the whole spectrum of light. And so we can use blue and we can use red. Now, we don't use red like we see. We use red that's a little bit outside of our eyes because that actually helps the scientists actually look at rocks and see different characteristics of the rock, like do they have quartz veins in there, or is there gold in the rock? I mean, it's not really gold, but we're looking for different structure within the rock, and that tells us a lot about what's going on in geologic factors that are on the surface of Mars.
And how do you calibrate these so that you can see these colors?
Right, so on the rover, we actually have what we like to call a sundial. And that sundial actually has some color calibration pieces. And so we'll turn our cameras toward that sundial, and we know what those colors are on Earth. So we look at them, we know it's red, we know it's green, we know it's yellow, we know it's blue. We can look at that sundial, we can actually calibrate to those colors, and then we can actually make a false color image that we can present back to Earth and say, here's what it would look like if you were looking at it on Earth, even though it's on Mars.
And that allows scientists to look for minerals that they're looking for.
Right. Look for different things, different structure in the rocks, yes.
Okay, great. Now, in order to get these rovers to Mars, they had to be pretty lightweight.
Yes.
And they are built of metal. And earlier I talked to Stan Siegel, who told us all about the metals that are on the Mars rovers. I am joined now by Stan Siegel. You are a titanium expert.
Well, sometimes they call me that, yes.
Now, why is titanium a good metal for aerospace industry and spacecraft?
Well, it's very important when you go into space, weight. And titanium has very high strength and a low density. And the combination of those two properties make it one of the most efficient metals in flight.
When you're working with titanium, it's more difficult than other metals. How do you make the parts for the spacecraft?
Well, basically, titanium is produced by all the same processes that aluminum and steel and stainless in forging, rolling, and extruding and things of that nature. There's no difference. Titanium is a little more difficult to work, and sometimes you have to use special care in handling it.
How do you find the best quality, and how do you test for that?
Well, there's 3 areas we like to test in. Once, when we melt the titanium as an ingot, we want to make sure the composition is perfect. So we take chemical analysis at various points in that ingot. We then process it to a bar product or plate, and we then take coupons and measure the strength and ductility. And then sometimes we will look into the part, like ultrasound in the medical field, and look for defects inside.
Oh, okay. Now, is the titanium used to build aircraft and spacecraft, is that pure titanium?
No, pure titanium has a strength of around 40,000. The most popular alloy is 6 aluminum, 4 vanadium, and 90 titanium. And that has 4 times the strength, and that's what's used on most aircraft and space. Small amount of pure titanium is used, but not very much.
Okay, so you have to combine it with some other things to make it useful for the aerospace
That's right,
industry.
and we call that alloying.
Okay. Stan, thank you so much for answering our questions today.
Well, it's my pleasure. Thank you.
It is time for my favorite part of the show, Stim It to Win It.
Hi, now I am joined by Patience and Lucas, and they are going to play our game. Now, here's what we're going to do. We're going to show you guys an image. It will either be an image from Earth or from Mars. When you think you know it, hit your button, okay? Are you ready? Let's take a look at the first image. Okay, Lucas, what do you think it is, Earth or Mars?
I actually think it's Earth because the rock doesn't look like it could have came from Mars.
Okay, so Lucas thinks it's Earth. Yeah. Our online audience says Earth. Let's see what our specialist Jim Zimbelman says.
Well, you've been looking at a view of Earth, looking at something called an alluvial fan. This is a process that's very common in deserts. It turns out there are alluvial fans on Mars, and the importance of that is it involves water carrying the rocks and debris to make the fans.
Okay, are you guys ready for your next image? Okay, ready? Here it is, Earth or Mars? Okay, Patience, what do you think it is?
Mars?
Mars? Okay, Patience thinks it's Mars. Our online audience thinks it's Mars. Let's see what Jim Zimbelman had to say.
So now you've been looking at an image of gullies on Mars. Why is that important? This is another form of water flow that's eroding these things, but gullies are not just Martian features. They also occur on the Earth where the same process is going on.
Okay, you ready for one more image? You guys ready? Here it is. Okay, Lucas, what do you think it is?
Okay, I think it's Earth again because it looks more like Earth.
Okay, so Lucas thinks it's Earth. Our online audience thinks it's Mars. Here's Jim to tell us what it is. Let's see if Lucas or the online audience is right.
Now you've been looking at ridges, topographic highs that have been caused by forces in the planet. First, you've been looking at Earth, but there are also many ridges on the planet Mars because the same internal forces are active there.
You guys did a great job. Let's go back to Kobe and Marty.
Thanks, Beth. Great job, guys. So, Kobe, how do we keep these rovers going so long? Because they've all outlived their lifetimes.
Yeah, it's a really good question. I wish I could tell you exactly. I mean, some of the things that we did, and I'll go back to Spirit and Opportunity, those were designed to last for 90 days. And, we've been on the surface of Mars exploring for 12 years with Opportunity, which is an amazing feat. And, there's a lot of testing that goes into the engineering. And, I mean, on all the sides, throughout the development, the design, the building, the testing, we've actually tried to make sure that we understood what was going to happen with the rover and make sure that we built something that was robust. But we never would have guessed that it would have lasted this long. And even with Curiosity, we made our primary mission, which was to last for 1 Martian year, 2 Earth years. And we've done a lot of great science, and we're getting all this great information back. But a lot of how we make them last is just to actually do really good engineering design. You start with fundamentals, you test it until you figure out where things break and how they break, you fix those, and then you actually get ready to send it to Mars.
So what's next? Are we sending something else to Mars?
Yeah, we are. We're sending a lot more stuff to Mars, which is quite entertaining and interesting. In 2018 now, we're going to send a mission called InSight. And InSight actually puts a seismometer on the surface of Mars. And so that seismometer is actually going to tell us the tidal effects, i.e. what happens here on Earth with the oceans and how they move. But we're going to see that on Mars with Phobos and Deimos, the 2 moons of Mars. And we'll actually be able to maybe tell if the subsurface of Mars is liquid or not. So does it still have a liquid core? And then the next one is another mission just like Curiosity with the same type of rover, same size rover, with a whole different science suite. It's called Mars 2020 at the moment. Hopefully it'll get a name soon. And it has one of my favorite instruments, it's a new science experiment. I'll call it a technology demonstration. It's called MOXIE. And what we're going to actually do is we're going to take the carbon dioxide in the atmosphere of Mars and convert that into oxygen.
Wow, and that's a first step towards actually sending humans towards Mars, isn't it?
You can start to lead into that if you'd like to. Yeah, I think it's very cool that we would be able to do that.
That's incredibly cool. All right, you ready for some questions?
Yeah, sure, let's do it.
All right, let's start with an online question. How long is Curiosity's mission and how long will its power source last?
That's a very good question. So the first part is the primary mission for Curiosity was supposed to be 1 Martian year, and we're going to drive up to about 20 kilometers. and 20 kilometers. And so we've done the primary mission in terms of time, not in terms of distance. We haven't driven that far, mostly because there's been really exciting science that's really close to where we've landed. How long is the source? Well, we have what we call a multi-mission radiothermal isotope. That's our nuclear source on that vehicle. And so its half-life is, I think, something like 37 years. So we're not going to have a power problem per se with that vehicle, but I don't actually know how long that power source will last, but I can sort of say about the half-life. So it has power for quite a long time. But just like the solar arrays on Spirit and Opportunity, as long as the sun's still giving us energy and we're pointing toward the sun, we still make enough energy for the rover to work.
Awesome. All right, we've got an audience question next.
Okay. Here you go. Come on up.
How quickly can a rover move?
How quickly can a rover move? That's a fantastic question. Let me do it in a way. Do you know what you know how big a football field is? Okay, so our rover Curiosity can do a football field in 45 minutes. So very slow. 5 centimeters a second is what we nominally say, but it takes about 45 minutes to go the length of a football field. So really, really slow. You wouldn't want to watch it drive. It's sort of like, oh, is it going to make it? Is it going to make it? So it's not very fast. But you know, it's 300 million miles away, depending on how you look at it from Earth. So there's no gas station, there's no somebody to fix it. So we can go slow because we have to process all the information. It's a great question.
Great question. All right, we've got an online question next.
Okay, another online one.
What made you want to design robots on Mars?
What made me want to design robots on Mars? Well, I mean, for me, it was actually in 5th grade. My 5th grade teacher really challenged me, and she asked me a question about what is it that I want to do. And I really, at that time, was into Star Trek. And I wanted to become Geordi LaForge. I wanted to be the engineer on the Starship Enterprise. And I thought it would be so cool to be the person that people go, hey, this is broken, can you fix it? And so that sort of started me on this career of doing engineering and being aerospace engineering, building vehicles that go to space. So that's really where I got my start. But I think it actually started before that. I just like working with my hands. I like seeing things and how they get put together.
That's really cool. Well, thank you so much for talking with us today. We really appreciate it. We'd like to thank the International Titanium Association for sponsoring the show today. And we want to encourage everyone to tune in next month as we take to the skies for one of my favorite topics, kites.
Hi, I'm Beth Wilson. I'm one of the hosts of STEM in 30. Did you know that every year the National Air and Space Museum hosts a Kite Family Day? And during this day, we bring in flyers who can fly kites indoors.
You can't fly a kite inside.
Actually, you can. In fact, the flyers refer to this not so much as flying a kite, but dancing with it. But no one steps on your toes.
I can dance.
You can barely nay-nay. If you think kites are interesting, be sure to join us for our next STEM in 30. Can you even fly a kite?
I've had trouble with that in the past, but we're going to call this show Redemption.
This should be interesting.
Thanks for watching. We hope to see you next month. I'm really bad at it.